Acids and bases, we are going to cover some definitions, the difference between strong acids, weak acids, strong base and weak bases, calculation for pH of strong acid versus weak acids, and then also look at the salt of the acids at the end of the PowerPoint. So common properties of acids that they have like a sour taste. They react with certain metals to produce hydrogen gas. They react with carbonates and bicarbonates. So these are basically not just common definitions. These are some of the keys that can help you to write the product of a reaction. So if the acid reacts with the metal, is going to give you hydrogen gas. So hydrogen gas would be one of the products. Then you can simply come up with the other product with the single displacement type reaction. And acids, when they combine with the carbonate or bicarbonate, they actually produce H2CO3, which is the carbonic acid as a result of single displacement or double displacement in this case. And since carbonic acid is not stable, is going to decompose, and when it does decompose, it will give H2O and CO2 as a product. And when it does say you have the carbon dioxide as a product, that's actually the byproduct of decomposition of the primary product. So you get the carbon dioxide gas as the final product. Bases with the bitter taste, they feel slippery, and some soaps or many soaps are basic. They contain base or they are basic. Simple bases, those are hydroxide compounds of group 1, hydroxide compounds of metals. And if you have a hydroxide of group 1A or 2A, it would be considered as a strong base. Some definitions for acids. Arneous acid is a compound that in water it would produce H+, and Arneous base is the compound that in water, if you add to water, it would produce hydroxide ion. So that is the first definitions. Then we have second definitions for Bronsted-Lowry acid base, which is based on compound accepting proton or donating proton. This covers more, because anything that classifies as Arneous is going to be actually covered under the Bronsted-Lowry definition as well. But this also covers a definition for acids and bases that you don't add to water. So if your compound donates proton, is going to be classified as acid. If it accepts proton, is going to be classified as a base. Why do we call H+ a proton? Because hydrogen has 1 electron, 1 proton, and 0 neutrons. So if we take zero neutrons. So if we take -1 electron, the only thing that is left is going to be 1 proton. So if you say H+ or proton, basically refers, or when you say proton, it refers to H+, because H+ has only 1 subatomic particle, and that is the 1 proton, because it didn't have neutron to begin with, and hydrogen had 1 electron. If it loses, it becomes the proton. So NH3 has pair of unshared electron. It can accept H+ or accept proton, and because it can accept proton, it will change to NH4+ and is going to be classified as a base. H2O, with respect to NH3, or when it's facing NH3, is going to lose H plus. So is a donor of proton donor. That's why it's classified as acid. We also have the definitions that we need to cover here based on the conjugate. We have a base after accepting H plus is going to change to conjugate acid, and acid would change to a conjugate base. The difference between an acid and a conjugate base pair is one proton only. So if you compare the H2O with HOH minus, this is like a one proton difference between the two. So this is called the acid conjugate base pair. So acid base pair or acid conjugate base pair, it's different by one proton only. And then you have the base. After accepting proton, it will change to conjugate acid. In this chapter, you're also going to learn more about the acid conjugate base. The stronger the acid is, the weaker the conjugate base. The weaker the acid is going to be a stronger conjugate base. Some properties of water, which is the acid-base properties of water, autoionization of the of water. For autoionization of water, if that means that of the same molecule, two of the same molecule is going to interact, and when they are interacting, one is going to lose hydrogen and the other one proton, the other one will gain proton. And then for the autoionization of water, your product is going to be hydronium ion and hydroxide ion. H3O plus is hydronium ion. You can represent this as H plus or H3O plus. And often H plus is going to join H2O in any aqueous solution, and it will change to H3O plus. Why is this happening? Because proton or H plus hydrogen is very tiny atom. Hydrogen is a very tiny, is the smallest atom of the periodic table. Handling a plus charge by hydrogen atom is very hard. As a result, it's going to join H2O, and when it does join H2O, is going to change to H3O plus. So in problem solving, and whenever they ask for concentration of H plus, or if they ask concentration of H3O plus, it's basically they are using interchangeably. So do not get confused if they ask for hydronium ion and then they are asking pH, and then you have to use concentration of the H3O plus or H plus. So it can be used interchangeably, but for any aqueous solution, H plus is not going to survive alone. It joins another H2O in order to survive. So you will get that combination as H3O plus, is also known as the hydronium ion. For the self-ionization or autoionization of water, which very small amount of the water is going to autoionize and it will generate hydrogen ion and hydroxide ion. You already know that concentration is 1 × 10⁻⁷, capital M, or mole per liter. That means only 1 × 10⁷ of that's a very small ratio. It's just that you see how small is this number. Very small ratio or amount of the water is going to ionize, and the concentration of H plus or hydroxide ion in pure water is going to be 10⁻⁷, 1 × 10⁻⁷, for both of them, for concentration of hydroxide ion and concentration of H plus for pure water. Now, if you add acid to water, concentration of H plus is going to increase, if you add base to water, concentration of hydroxide ion is going to increase. But at any given time, the concentration of H plus times concentration of OH minus at 25 degrees Celsius is going to be 1 times 10 to negative 14. This is for any aqueous solution. For pure water, concentration of H plus equals concentration of hydroxide ion, and that equals 1 times 10 to negative 7. In acidic solution, concentration of H plus is higher, so OH would go down. In a basic solution, concentration of OH ion is higher, so H plus is going to be lower. And the concentration of OH and H plus is related by this equation here for any aqueous solution. For pure water, 10 to negative 7, and the pH for pure water is 7 because you take negative log of this number for concentration of H plus. But for acidic and basic solution, the concentration is going to change because you have an external effect. You have added either acid or base to change the concentration. So we have the ion product. This also helps you more understanding previous chapter when we are talking about equilibrium. When you are writing equilibrium expression, pure liquid and solid is not allowed, so we should not write the H2O. So Kc is going to be concentration of H plus and times concentration of hydroxide ion. And this is like very specific to water, and that's why it's known as a Kw. So Kw is the same thing as a Kc, but is for water, is the Kc water, so we call it Kw. The value for Kw is 1 times 10 to negative 14. That's for pure water and for any aqueous solution. So, if concentration of HCl is given to us, we try to find concentration of OH minus. We are using the Kw, and concentration of H plus we assume to be 1.3. Why? Because you probably know already, and you will learn more about it in this chapter, that HCl is a strong acid and is going to 100% dissociate, and it gives H plus and Cl minus. So if you have 1 mole of HCl, you would get 1 H plus and 1 Cl minus. If you have 1.3 molarity, you will get 1.3 molarity of the H plus, and you would get 1.3 of Cl minus. So for a strong acid like HCl, it is correct to assume that concentration of H plus equals concentration of the molecular acid for monoprotic based on the balance equation that we have here. So we have the concentration for H plus 1.3. We have the value for Kw, which is 1 times 10 to negative 14. And that's how we calculate concentration for hydroxide ion. Again, the concentration for hydroxide ion, it should be lower than the concentration of H plus. So if you find this number to be greater than 1.3, right away you know you've done something wrong. So make sure you test your answer yourself, make sure that it makes sense. So this number is lower than the concentration of 1.3, is lower by a huge and significant value, and that is understood because this is a strong acid, and in a very strong acid like HCl solution, concentration of hydroxide ion is expected to be low, so it is low, and that's what we are looking here for, making sense of the answer that you find in your calculator, because if you don't put this negative sign there in your calculator, then you are going to find a much higher number for this. So I'm just trying to make sure that you check your answer, make sure they make sense. Okay. Calculating pH is negative log of concentration of hydrogen ion. So for neutral solution, pH is 7. For acidic solution, because concentration of H plus is greater than OH minus, so concentration for H plus is greater than 10 to negative 7, so pH is going to be less than 7. For basic solution, pH is going to be greater than 7. Why is greater than 7? The pH is greater than 7 because concentration of H plus is less than 10 to negative 7. It could be like a 10 to negative 9, then pH is going to be 9. If it's 10 to negative 10, then the pH is going to be 10. So these numbers are smaller than 10 to negative 7. So just make sense of the number. As the concentration for H plus is decreased, pH is going to be higher because you're taking negative log of the number. So the negative log of this number is 10. Negative log of 10 to negative 9 is 9. POH, the calculation of the POH is also similar to pH, but now you're using the concentration of hydroxide ion. If you have the pH, you can calculate POH. pH plus POH equals 14. So if you have the pH already to be 4, pH of 4 plus POH is going to be 14. This is just a hypothetical number. Then POH is going to be 10. So basically you are calculating, you can calculate the pH if you have POH, if you have the pH, you can calculate the POH if you have concentration of the hydroxide ion as well. So if you have concentration, you can calculate it. If you don't have the concentration, you have your pH, you can calculate it. If you have concentration of H plus, you can find concentration of hydroxide ion and then take the negative log. Or, so if you have H plus, if you have this value, you can then find concentration of hydroxide ion, then take the negative log of concentration of hydroxide ion to get the POH. That's one way. Another way you could do, you could take the pH, find the pH using the concentration of H plus, and then say 14 minus a pH equals POH. So you have to see which one is the shortcut. So especially for multiple choice questions, both ways is going to be correct. If you have the pH, you can calculate the concentration of H plus. Concentration of H plus. So this is the time that you have the pH already. Concentration for H plus is going to be 10 to the value of 10 to the power of minus pH. So if the concentration, if the pH is 3, pH equals 3, then concentration of H plus is going to be 10 to negative 3. So you can, they are just different way of, because it's a scientific problem. So it's not just a single way to answer the question. So you can do, you can get the concentration from the pH, or the concentration could be given to you, or concentration of the acid could be given to you, but you have to make sure that the acid that is given is a strong acid if you want to use the number directly. If it's weak acid, just like the equilibrium expression for other compounds, for any chemical reaction, you can write equilibrium expression for your acid, weak acid. pH can be calculated from concentration of H+. pOH can be calculated from concentration of the hydroxide ion. If you have the pH, you can find the pOH using this equation also. Do you have any questions? If you have any questions so far, you can use the chat option for your questions. You let me know about your questions. I make sure that what I'm talking about is clear to you, and is also, I'm moving in the right pace, so I'm not moving too fast. Okay. When we talk about strong acids, 100% dissociation, we talked about the HCl dissociating 100% because HCl was a strong acid. So in water is going, you will see this single arrow here. That is a strong acid. Strong acids are strong electrolyte because they dissociate and they produce ions. 100% dissociation is going to produce 100% of the ions. So these are some of the strong acids. We have 6 strong acids. You have to memorize those 6 strong acids, and then you have to, for any acid that is not one of those 6, you would say those acids are weak acid. That's how you recognize if the acid is a strong or weak. The question is not expected to tell you if the acid is strong or weak. You have to recognize it. How do you recognize it? Just look at the name for the, if it's one of the 6, strong acid is a strong. If it's not one of the 6 strong acid, then it's going to be weak acid. So for weak acid, you have a double arrow. That means it's not 100% dissociation. Some of the acid will change to, this is the AQ. Some of the acid is going to change to ions, and the rest of the acid is going to stay in the molecular form intact. So in a weak acid, you find H+, you find the anion coming from the counterpart of the acid after losing the H+, which basically is the conjugate base, and you find the molecular form of the weak acid. For a strong electrolyte, when you have 100% dissociation, this would change to 0 after you add to the water. So if you have 1 mole of this NaCl, it would change to 1 mole of Na plus and 1 mole of the Cl minus, 100% dissociation. For weak acid, you see double arrows. These are some examples of weak acids. That's not one of the 6 that you should memorize. Okay, so nitrous acid, and this is a weak acid, and it's showing with the double arrow. That means that it reaches equilibrium, and when it reaches equilibrium, you have acid, you have the conjugate base, and you have H+ mixed in the reaction mixture. Strong bases, single arrow, that means 100% dissociation, strong base. And pay attention to this balanced equation. For barium hydroxide, for 1 mole of this barium hydroxide, you're going to get 2 moles of hydroxide ion, 1 mole of the barium ion. But for monoprotic base like this, if you get 1 mole, it's going to change to 1, and then this is 1. So for a strong acid or strong base, you have to pay attention to the balanced equation, because you cannot just assume that barium hydroxide concentration would be same as concentration of hydroxide ion because of this coefficient of 2. Weak bases again. Weak bases are weak electrolyte. and because they are weak electrolyte, they are going to reach equilibrium. That means that is not 100% dissociation here. So you will get a mixture of the reactant and product at the equilibrium. So if you have a weak base like this, you're going to get mixture of all four species. Pure liquid is not going to appear in the K equilibrium expression, but you have some of the reactants left. The conjugate acid-base pair, the stronger the acid is, the weaker the conjugate base is going to be. H plus is the strongest acid and hydroxide ion is the strongest base in aqueous solution. So we have a strong base here, strong base. That means the conjugate acid is the weak acid. Weak acid and strong conjugate base. So strong conjugate base from weak acid. Same thing here. Weak acid, strong conjugate base. These are the 6 acids that you need to memorize. Okay? You need to memorize these. And then let's say you see hydrofluoric acid is one of the 6, so it's going to be weak acid. HCN is not one of the 6, then it's going to be weak acid. So that's how you determine if the compound is acidic or it's basic, or if it's strong acid, it's a weak acid. So you're talking about the memorizing these six acids. How is strong acid different from the weak acid? Showing at the molecular level. If you have a strong acid, concentration of the H plus and the minus, in this case like for HCl, is going to be equal. The dissociated part is equal. This is 100% dissociation. In the solution, you are not going to see any HCl. These are only Cl minus and H plus that is floating in the water. So you don't see any HF here. You don't see any HCl here. But for weak acid like HF, some of the HF molecules are still shown in the mixture. So these are your acid that is left, and you have some of them that have been dissociated. So only one has been dissociated after there's 6 of them. See? One is being dissociated, so you have the fluoride ion. But in this case, all of them has changed to chloride ion. There is no HCl left. pH of 2 times 10 to 3 molar HNO3. What do we know about HNO3? HNO3 is one of the 6 strong acids. So it's right here. What does it mean? It means that it's going to dissociate 100%. And if it does dissociate 100%, concentration of H plus equals concentration of HNO3. That's what it means. Okay? So if you have the concentration, and because it's monoproduct, it's going to be equal. You have the concentration of the H plus, you take a negative log of the concentration of H plus in order to get the pH. Negative log of concentration of H plus. Again, H plus and the hydronium ion in aqueous solution, it means the same thing. Because H plus doesn't survive on its own or is not very stable, is going to add to the molecule to give you H3O plus. Barium hydroxide. What do we know about barium hydroxide? It's a strong base. And when it does dissociate, it's going to give you 2 hydroxide ion and 1 Ba2 plus. So concentration of hydroxide ion equals 2 times concentration of barium hydroxide. So you have to pay attention to that. You are given the concentration of the barium hydroxide initially at the start. The after it does dissociate, you get 2 times concentration of the barium hydroxide as concentration of hydroxide ion. Then you can have the concentration of hydroxide ion. The question is asking for pH. You have 2 ways to deal with this. Either find the concentration of H plus using Kw. So concentration of H plus is Kw divided by concentration of hydroxide ion. Then you take negative log, or just negative log of the concentration of hydroxide ion, which gives you POH, and then you subtract that from 14 to get the pH. What happens if you have a weak acid? Any questions so far for a strong acid or a strong base? How do you calculate pH or POH? Any questions? If you are attending the class, you're logged in, and I just want to make sure you have, I answer your questions at the same time. If you don't have any questions and you hear me, please just say no questions. Make sure that you don't have questions. No questions. Okay, good. Weak acids and ionization constant, or Ka, which is the equilibrium constant for weak acids. You do not have Ka for strong acid. Why have a Ka for strong acid? Because if you write Ka for strong acid, like HCl, is going to be concentration of H plus, because it's product over reactants, right? Cl minus over concentration of HCl at equilibrium. Well, this reaction does not reach equilibrium because it's a strong acid. It doesn't reach equilibrium. So we don't have equilibrium. We cannot write this. If you assume that it would reach equilibrium, by mistake, you write this HCl concentration after you mix the HCl with water is going to be 0. And any number divided by 0 is not a defined number. So Ka does not make sense for strong acids. You only write the Ka for weak acids only. So it does up to weak acids only for Ka. So when you say Ka is the concentration of product over the reactant, you learned this from previous chapter, concentration of product over the concentration of reactant. You don't involve the H2O here because H2 is liquid. It's liquid, or pure liquid. So you don't involve that H2O here because it's a reactant, products over the reactant. So we have this. Now, Ka at a given temperature, at room temperature, is recorded in the books. So we have the value of Ka for many acids. If we have the value for Ka, we can, if the concentration for Ha is given to us, this is the concentration of the acid, then we can find the concentration for H plus. Because concentration for H plus, you see this here, concentration of H plus is going to be equal, exactly. Solids are not included either. Solids and liquids are not included. Very good. Concentration of H plus equals concentration of minus for the weak acid. And this is just a representing formula. So concentration of H plus equals concentration of the conjugate base for monoprotic weak acid. So if this value is X, this value is also X. So Ka is going to be X squared or concentration of HA. Now, for any given problem, if the value for concentration of the acid is given initially, the value for Ka is known, you can find the value for X. And then we take multiply Ka by this concentration, take a square root to find the value for X. And that X is concentration of H plus. Concentration of H plus, then you can take the negative log of that to get the pH. So the key is to be able to write the Ka value for the Ka expression for a weak acid and understanding Ka. The greater the Ka, what does it mean? It means higher value for H plus concentration compared to the HA concentration, and that means a stronger acid. So a stronger acid among the weak acids. So which one is weak? Which one is weaker? Which one is the stronger of the two weak acids? That's what we're talking about. We're not saying that a strong acid versus weak acid. A stronger weak acid. So the values for Ka, as I said, they are given at the 25 degree. 25 degree in science, in chemistry, is known as the standard temperature, and also known as the room temperature. If this temperature changes, the value for K is going to change. So that's why when they are given the Ka, they give that Ka in certain temperature. So we have these values. Which one is stronger? Hydrofluoric acid or nitrous acid? Which one is stronger? HF or HNO2? Which one is stronger? HF is stronger because the value for Ka for HF is higher than the value for Ka nitrous acid. The exponents are the same, so you only compare the coefficients. When the exponents are the same, the smaller the coefficient, the smaller the value. So you don't have to compare these two, you just compare these two because they are the same. So HF is stronger. Ka for HF is greater than Ka for nitrous acid or HNO2, so HF is stronger. Which one is stronger? Acetic acid or benzoic acid? Acetic acid versus benzoic acid. Which one is stronger? So you're going to compare these two numbers because the benzoic acid, very good, because benzoic acid has higher Ka, is going to be stronger than the acetic acid. So that's what all it means. Previous slide, because if it didn't make sense here, what does this mean? Means that if you are given the values for Ka, the one with greater Ka is the stronger weak acid than the other one. So all of these are weak acid. How do we know all of them are weak acid? Because you have value for Ka. If it was a strong acid, you didn't have the value for Ka. Ka times Kb equals Kw. That's another. Ka times Kb equals Kw. So if you have the value for Ka, you need the value for Kb, you're going to set up that number times 1 times 10 to negative 14, which you have to memorize this number. Kw, or concentration of H plus and hydroxide ion for pure water, is constant number at room temperature. So you need to know this number. If you know the number Kw and you are given Ka, you can calculate Kb for the conjugate base. So Ka for an acid times the Kb for the conjugate base equals Kw. Okay, how do you find the pH for weak acid? You are going to set up ice again. What is ice is the initial value given, change, and then concentration at equilibrium. The initial value, you have to find these values in a problem, given problem. So you are given 0.5 molar HF. Initially, we say there is no H plus and F minus until dissociation takes place. Okay? When dissociation takes place, X number of HF is going to dissociate. So we have a negative because this is the reactant. Then we have X. If we get X of these dissociated, X of H plus and X of the F minus is going to be produced. These are going to produce an increase in concentration. That's why we have a plus X for them. At the equilibrium, X value would be deducted from the initial value for HF. So we have 0.5 minus X. Minus X means that the concentration over the time of the reaction of HF is going to decrease. So when you add HF to water, basically you are adding 0.5 molar HF into water. Some of it is going to dissociate and it gives H plus and F minus. Basically, some of that is to be consumed. So by the time it reaches to equilibrium, concentration of HF is going to be decreased by X. Concentration of H plus is going to increase by X, and increase by X. Since we started from 0, then the equilibrium value for these two is going to be X. So you set up ice. I'm sorry, I think I already said that clearly in previous chapter. You set up balanced equation first for dissociation of the acid. Then you set up the ice. Then you write the equilibrium expression. Equilibrium expression is concentration of products over concentration of reactant raised to the power of coefficient for reactant and product. Since it's 1, we don't have to write it, but they're all 1 in this case. Then to solve for X or solve for concentration of H plus, basically when you find the value for X, you are going to basically find concentration for H plus. If you have the value for X, you find concentration for F minus. They are the same values. You are going to replace the concentration at equilibrium into the K expression or equilibrium expression for acid. You are going to find this expression here. Ka is x2, 0.5 minus X equals the Ka value, which is given to you. After you solve this, you are going to get like a quadratic equation. Often, you can simplify this and say this value, because if the value for X is going to be small, then the value of compared to the given value for the acid, if it's very small, you can just say it's not significant, and you can approximate this value to be 0.5. 7.1 times 10 to 4 is a constant number, and it will be given to you, yes. Unless everything else is given, and that is the question. maybe for different temperature. If you have the concentration of X, and HA, then you can find it at different temperature. But this is a constant number, and you're right. This is a constant number, and it will be given to you, 7.1 times 10 to negative 4. Yes. And because this is a small number, the K value, it's assumed that X is going to be a very small number. And if X is a very small number, you can say this approximation is valid. So you can approximate this, and you can solve it. This is a simpler. It's going to be much simpler if you approximate it. So Ka times 0.5 equals x2. So x2 is going to be, then you take a square root of x, this value to get value for x. And this x, what is that x? Is the concentration for H plus, is the concentration for F minus. The question is asking for pH, so I don't need to say this is equal to concentration F minus. But if the question asks you what is the concentration of F minus, then you say is the same number. Okay, so concentration of HF, concentration of F minus equal, and that is the value that you found for X. To find the pH, you take negative log of this concentration, and you get the pH for this given for acid. Now, exact value that you find, or more precise number you find for HF, you would use this 0.5 minus X. If you have the value for X, you subtract, and this would be the concentration at equilibrium for HF also. Now, how do you know your approximation was correct or not? What you could do, you could say the value of X over HA times 100. If is less than 5%, then your approximation is correct. If this value that you find for X is going to be large number in a way that the percentage is going to be greater than 5%, then your approximation was not valid, and you have to go back, do not approximate, and solve a quadratic equation. Okay, it's right here. So this value is 3.8 when you find the value for X comparing to the initial value for HA. If it's less than 5%, then your approximation is okay. Now, we have a different example here. You are going to use 0.05 molar instead of the 0.5 molar. You approximate the 0.05 minus X to be like 0.05, and then you solve for X. When you solve for X, now you find the value for X. X over HA is greater than 5%. Your approximation is not okay. And if the approximation is not okay, then you have to solve your quadratic equation. How do you solve the quadratic equation? You're going to, I had one example in the previous chapter. So what you're going to do, you're going to say this minus X equals x2 over 0.05 minus X equals 7.1 times 10 to this. And then you're going to multiply and bring the like terms, and you are going to have the ax2 plus bx plus c equals 0. You set up your quadratic equation, and then use the x, you find the x for the quadratic equation. I do have example here also. Okay, show you. So this is the summary of what we have been doing so far. Identify the species that can affect the pH. Water often is ignored. the H plus that is coming from water because it's very small value. And also OH is going to be much smaller than 10 to negative 7 in acidic solution. Because it's acidic solution, concentration of H plus is going to be greater than 10 to negative 7. So concentration for hydroxide ion is going to be less than 10 to negative 7. So small number, you can ignore that also. You set up the ice, you solve for X, and when you solve for X, if the approximation is not valid, then you have to solve for X exactly without approximation, basically solving quadratic equation. Okay, Ka is 5.7 times 10 to negative 4. Can we approximate X or not? Is not very small number, so we're going to try. If we approximate, so if we are going through the whole process again, just as a review, you have your balanced equation first. That's the step 1 first. Second, set ice. I don't write it horizontally, I write vertical because that's how you are setting up. Initial values for HA was given. Initial value for either one of these would be 0 because it doesn't give any value to begin with. We have the value for Ka. So we are going to set up the ice, decrease in concentration, increase in concentration, and then set up the Ka expression. Ka expression in this case is going to be H plus A minus over HA. So we have the K expression. Then use the values at equilibrium to replace it in the K expression for acid. Value for Ka is given to us, is a 5 times 10 to negative 4. X, and this one is going to be 0.122 minus X. If we approximate X value, then we can say this is going to be equal or approximately as 0.122. You approximate, you find the value for X, we calculate the percentage is greater than 5, so our approximation is not valid, so we have to find the X exactly. To find the X exactly, we don't approximate this. We are going to set up the quadratic equation. Where is this coming from? Is X2 equal to this? So basically you rearrange this to say X2 equals 0.122 times 5.7 times 10 to negative 4 minus 5.7 times 10 to negative 4x. Then you bring everything to the same side to make it equal to 0. So it's going to be x2. This number times, when you have to do this multiplication first in order to bring it. And the proper format is the x2x and then no x here. So we're going to write this one first. The negative sign, you are moving over to this side, is going to change to positive. So it's going to be plus 5.7 times 10 to negative 4x. This number is positive. When you move it over, it would change to negative. So we have minus 6.95 times the negative 5 equal to 0. That's how you set up your quadratic equation. So you basically do the cross multiplying and you bring everything in descending order of x and equal to 0. If you are moving any variable from the right side to the left side of the equal sign, the sign is going to change. If it's negative, it becomes positive. If it's positive, it becomes negative, equal to 0. Now you have the format for quadratic equation. You memorize this again. This is a shortcut. And then you're going to find the value for x. You find two values for x, plus and minus. Minus, that means less than 0. It doesn't make sense. So you are using the plus one. Percent ionization, that's like what percent of the HA has been ionized. For a strong acid, it's 100%. For weak acid, it depends on the weak acid. If it has high Ka, higher percentage is going to be ionized. Any questions so far? So basically you find the value for x, you divide by initial value of the acid times 100, that gives you percent ionization. No questions? For weak base, you treat it just like weak acid, with exception that now you are calculating for HA, I'm sorry, for hydroxide ion instead of the H+. You're not going to bring in H2O because it's pure liquid. You write K expression for, or equilibrium constant expression for base. That's why we call it Kb. Is the same thing as Kc for any equation based on the concentration. But since we know this is the base, we can name it as a Kb. Concentration of product over concentration of the reactant. And the higher the value for Kb, stronger the base is going to be. Kb, you can take negative log of Kb and you get a pKb. If you take negative log of Ka, you would get pKa. pKa, just like pH. pKa smaller, what does it mean? Smaller pKa means stronger acid. Is different from Ka. The large Ka means stronger acid, but the smaller pKa means stronger acid. It's just like pH with concentration of H+. The higher the concentration of H+, the pH is going to be a smaller value because of that negative log effect. Kb value, again, Kb times the Ka for conjugate acid is going to equal to Kw. So if one is given, the other one can be calculated because you have this number as 1 times 10 to negative 14. Which one is a stronger base? Ethylamine or methylamine? Ethylamine is a stronger base because the value for Kb is higher. Okay, very good. So we have these values also given to us, and it will be given in a problem when you are solving the problem. Then Ka times Kb equals Kw. If Ka is given, you can calculate the value for Kb. If Kb is given, you can calculate the value for Ka, because the Kw is a known value, 1 times 10 to negative 40. If you have a diprotic acid, that means one acid molecule, H2SO4, has 2 protons. This can ionize in 2 steps. First, you're going to get H plus and HSO4. Then H plus, from this, you would get H plus and SO4 2 minus. So 1 proton at the time would leave the acid. If you have more than 1 proton, it's known as a diprotic acid. The first step is going to be fast. So this is going to have a large Ka, but we don't have it because H2SO4 is a strong acid. But if you go from HSO4 minus to H plus and SO4, you have a Ka value here, given Ka value. So if you have 2 steps, if the first one is a strong acid, you don't have the Ka value, but for the second one you have. Or if that's for a strong acid. If it's a weak acid, then you could have both numbers, but the first one is going to be greater than the second one. Like oxalic acid, you have 2 H's. This is acidic hydrogen, that's another acidic hydrogen. If you loses one of the hydrogen, the Ka is higher than losing the second one. So it's just understanding that diprotic acid, they lose hydrogen 1 at the time, and the first one is lost faster than the second one. Basically, when you say a strong acid, that means it can lose hydrogen easily. So if it loses hydrogen easily, that's a stronger acid. Phosphoric acid has 3 hydrogens, so it can actually lose hydrogen in 3 different steps. And each time you see that the Ka value is decreasing. And this is much lower, significantly lower than the first one. Between these two, you have some, it's close, but this is a minus 13, which is a much smaller value. What factors affect the strength of the acid? The stronger this bond is, the weaker the acid is going to be. That means it doesn't want to lose the H plus. So in a group 7 for halogens in a periodic table, if you look at the order in periodic table, you have the fluorine, then you have chlorine, bromine, iodine. Up, down, the acidity is going to increase. The acidity is going to increase because they can lose hydrogen easier. The bond is weaker for Hi compared to Br, Cl, and Bf. So it can be explained this way, or you can say the size factor. In a group, as you move up, down, the size is increasing, acidity is going to increase also. The larger the size, easier to handle that negative charge. So Hi, when it loses hydrogen, is going to change to H plus and I minus. I minus here, it's larger anion with the negative charge compared to HCl. When it loses, it changes to Cl minus, you have a smaller size, chlorine, iodine. For this large molecule or large anion, it's easier to handle the negative charge compared to the chloride ion. This is another way of saying it, but I tried to say it in different ways, so hopefully one way is going to stay with you. You can just say in a periodic table, in a group, as you move up, down, acidity is going to increase. H2O, H2S. See, acidity is going to increase. Hydrosulfuric acid, but this one is just water. So acidity is increasing up, down in the periodic table. Electronegativity of the atom that is attached to the greater the electronegativity, the stronger the acid is going to be, and oxidation number. The higher the oxidation number, the stronger the acid. This is the oxidation number of the atom that carries ionizable hydrogen. So this hydrogen is going to leave easier if the oxidation number for zinc, or Z is not zinc, sorry, for this Z element, which is a representative element, that could be the carbon here or the nitrogen, the higher the oxidation number is going to be stronger. So between these two, nitrous acid and nitric acid, which one is stronger? There is no change in electronegativity, but oxidation number is different. This one has 3 oxygen attached to it, is more oxidized, so a stronger acid. Nitric acid is stronger than nitrous acid. Nitric acid is one of those 6, is actually a strong acid, but nitrous acid is a weak acid, is not one of the 6 strong acids. Phosphoric acid is stronger than phosphorus acid because here you have 3 oxygen attached, you have 4 oxygen attached. So you can also compare them. If you have the oxy acid from the same group, the electronegativity, the higher the electronegativity, the stronger the acid is going to be. This is for the oxy acid. So some other trends that it can help you to answer multiple choice questions. Oxy acids that they have greater number of oxygens is going to be stronger. Okay. So oxidation number is higher and you have greater number of oxygens attached. So if you have oxy acids, that elements are the same except the number of oxygen. The greater number of oxygen, basically greater number oxidation number for the central atom, and a stronger acid. For some of the questions that I saw in the assignments is dealing with is the salt solution acidic or basic? How do you know the salt solution is acidic or basic? Depends on is coming from strong acid, weak acid, with what combination? Okay. So if your solution, if it's coming from a strong acid and a weak base, the solution is going to be acidic. If it's coming from a strong base and weak acid. This is a salt. How do we know it's a salt? Because it's a metal and non-metal. So you have a metal, non-metal. With the metal, non-metal, this actually should be no hydrogen here. So it's a sodium acetate. metal is coming from base. This part is coming from acid. How can I change the to base? I'm going to say NaOH. Add the OH to this, it's going to be base. Add H to this one, it's going to be the acid. So this is going to be weak acid, strong base. So if it's coming from a strong base and weak acid, the solution is going to be basic. Why is that? Why is basic? Because the weak acid, when it dissociates, is going to give us a conjugate base, and this conjugate base is going to hydrolyze. If it's coming from strong base, it's not going to hydrolyze. Only the weak part is going to hydrolyze. So NaCl is coming from NaOH and HCl. Is coming from a strong base, is not going to hydrolyze. Is coming from strong acid, is not going to hydrolyze. So this is going to give us neutral solution. So if the solution is coming from a strong acid and a strong base, it's going to be neutral. If it's coming from a strong base and weak acid, it's going to be basic. And if it's coming from strong acid and weak base, then it's going to be acidic. So strong acid with weak base, your solution is going to be acidic. A weak base, strong acid. So it's coming from strong acid and a weak base. Our weak part, the part that is coming from weak, is going to hydrolyze, and when it does hydrolyze, it can give up, it can make the solution acidic. If you have Al3 plus, this is acidic because it's looking for electrons. That's one of the exceptions to the, let's say you have like AlCl3. If you draw the Lewis structure for that, you're going to get this Lewis structure. Cl, that's aluminum, and Cl. That's the Lewis structure for AlCl3. There is no electrons left to give to aluminum. This compound exists, but is not satisfied based on the octet rule. It has empty orbital. Empty orbital, it's acting like acid. So if you have this as part of the salt, it's going to give you acidic solution. So this is one of the exceptions. You may not get it too often, but just, for one multiple choice questions or something. So basically, it's going to take hydroxide in order to satisfy the octet, and is going to leave H+. So it's taking the hydroxide from water. If both of them, if it's coming from weak base and weak acid, what would be the salt solution? Is it going to be acidic or basic? It depends on the weak base is stronger or the weak acid is a stronger acid. So if it's coming from a stronger base, how do we know a stronger base? Stronger base meaning it has higher value for Kb, or it's coming from a stronger acid. The cation is coming from acid in the salt. The anion is coming from the base. So you would look for the Kb for anion and Ka for cation. And then you can decide it's going to be acidic or base. It has some memorization here involved. Basically, that would be the magic. There's really nothing that we can, but it also makes sense. If it's coming from a stronger base, weak acid, the solution is going to be basic. If it's coming from a strong acid and a weak base, then the salt solution is going to be acidic. So basically the strength of the stronger piece is going to carry over into the solution. And with like 4 or 5 different examples, you can come up with this conclusion yourself. So you can say the strength of the original strong acid or base, it can carry over into the solution. That makes it easy for you to get it. So if you get the salt that is coming from a strong acid and a weak base, the salt is going to be acidic. If it's coming from a strong base and a weak acid, then the salt is going to be basic. And this one, if both of them are weak, then you have to look for the exact value for Ka and Kb. The hydrated cations, this is for the examples of iron and aluminum. These are basically the only ones that you have to be worried about. Highly charged then is going to give you acidic salt. Oxide of metals is going to give you basic solution. Oxide of non-metals would give you acidic. And then amphoteric, these are the compounds that they can act both for acid and like base. Where do you find them, or when they are going to be acid is time that you can see the facing stronger base, then they would act as acid, or if they're facing a strong acid, they would act like a base. So it depends on the other part. One more time, definitions. Arneous acid is going to produce hydrogen ion. Arneous base is going to produce hydroxide ion. Bronsted acid is going to donate proton. Bronsted base is going to accept proton. Lewis acid will donate or pair of electrons, accepts pair of electron, like aluminum that I said is a deficient in electrons. Because it's deficient in electrons, it has empty orbital. This can take pair of electrons, so this is acid because it's empty orbital. So if it has empty orbital or it can take pair of electrons, is acid. If it can donate pair of electron, like ammonia can donate pair of electron, it's going to be base. Borane, again, write the Lewis structure for BF3. Is going to look like this. Empty orbital here. There's empty orbital, and that empty orbital is ready to accept pair of electrons, so it's acting as acid. This is donating pair of electron. Ammonia is base. Accepting pair of electron is acid. Okay. Any questions that you might have before I stop recording that might benefit other people? Any questions? Okay. Going to